Section 4.2, Logarithmic Functions. Here is the definition of the logarithmic function. We have y equals the log to the base b of x. X must be greater than 0. B needs to be greater than 0 and not equal to 1. And this is equivalent to the exponential expression b to the y power equals x. The function f of x equals the log to the base b of x is called the logarithmic function with base b. These two different forms are actually equivalent ways of showing the same mathematical concept. Much like the number 5 could be written in Roman numerals with a v, but it would still be 5. Logarithmic and exponential functions carry the same concepts. In exponential form, you're used to the base being raised to the exponent. In logarithmic form, we write the base in this location, and logs are exponents, so the log equals the y, which is the exponent. In example 1, each expression in logarithmic form, we have to write it in exponential form. So looking at this first one, the base is 7. So this expression means that we have a 7 as a base. Logs are exponents, so the exponent is 3, and that equals the argument of the log, which is x. In example B, the base is b, so we write the b down below. The exponent is 2, and that equals 25. In this third example, we have a base of 4, so we write 4 to the y equals 26. Notice in the first two examples, you might be tempted to do a bit more work. For instance, where it says x equals 7 cubed, you might feel like you should compute that out, but you don't need to. And b squared equals 25, you might notice that b would be 5. All they're asking us to do is to change forms. We don't have to do any other work at this time. Now let's look at some examples where we go the other direction. These three examples are in exponential form, and we want to write them in logarithmic form. This first example, we get 5 equals log base 2 of x. Notice that the base is 2, so the base of the logarithm is 2. The power is 5, and since logs are exponents, the 5 is written in this location. And we get 5 equals log base 2 of x. Next example, again, the base was b, so we write the b down here. The exponent is 3, so that gets written on the other side, and it's log base b of 27. In this third example, e is the base, the exponent is y, so we get y equals the log to the base e of 33. In example 3, this first problem, log base 10 of 100, since logs are exponents, we're wondering what power do we have to give to 10 to get 100? And you might recognize that 10 squared gives us 100, so this expression is equal to 2. In the next example, what power do we have to give to 5 in order to get 1 over 125? To start this one out, you have to recognize that 125 is 5 to the third power. But the answer isn't 3. We have a 1 over 5 to the third. So you need to recall that negative exponents give us reciprocals. So the reciprocal of 1 over 5 to the third is 5 to the negative 3. So we have to give 5 a power of negative 3 in order to get 1 over 125. So the answer is negative 3. In this next example, we have the log to the base 36 of 6. This means 36 to what power gives us 6? Now, if you go into this one too quickly, you might think the answer is 2. But it's 6 to the second power that gives us 36. We need to know what power that we have to raise 36 to get 6. So you'll need to recall that the square root of 36 is 6, and that square roots can be equivalently written with a power of 1/2. So 36 to the 1/2 power is equivalent to the square root of 36, which is 6. So that tells us that the answer is going to be 1/2, because 1/2 is the power that we have to give to 36 to get 6. In this example, we have the log to the base 3 of the 7th root of 3. Now, in much the same way that the square root gave us a 1/2 power, a 7th root gives us a 1/7 power. 3 to what power gives us the 7th root of 3? The answer will be 1/7, because 3 to the 1/7 is the same as the 7th root of 3. Here are two logarithmic properties. The first one says the log to the base b of b equals 1. This says that if the base is the same as the argument, that logarithm will always equal 1. If you change it to equivalent form, that's b to the first equals b. And then our other property that involves 1 is the log base b of 1 always equals 0. Notice if we change forms, that gives us b to the 0 equals 1. And you should recall that any base to the 0 power gives you 1. Let's look at some examples that involve these properties. The first one, log to the base 9 of 9. Well, we saw that if the base is the same as the argument of the log, that you always get 1. So therefore, the log to the base 9 of 9 must be 1. Remember, logs are exponents, so we're asking what exponent do we have to give this base of 9 to get 9? And 9 to the first power is 9. In the second example, we have the log of a base and the argument is 1, so we must get 0 as a result. So the log to the base 8 of 1 is 0. The property tells us that, but we can also think about the equivalent form. 8 to what power gives us 1? Well, anything to the 0 power gives us 1. Now we have two inverse properties. The first one is the log to the base b of b to the x equals x. This says that the logarithm with the base b of b raised to a power equals that power. The second one is b raised to the log base b of x always equals x. b raised to the logarithm with base b of a number always equals that number. Here's the summary of those four properties. Let's look at some examples. This first example is an example of the base of the logarithm being the same as the base of this exponent to a power, so we get that same power. So therefore, the log to the base 7 of 7 to the 8th is simply 8. If you think about changing forms, logs are exponents. We're asking what exponent do we have to give 7 to get 7 to the 8th power? Well, we'd have to give it an exponent of 8 to get 7 to the 8th power. This next example fits into this pattern, and so we can conclude that 3 to the log base 3 of 17 must be 17. Again, 3 is being raised to an exponent. That exponent is the exponent you have to give 3 to get 17. And since we're giving that exponent to 3, we must get 17. You can think these through each time, but it's probably best to simply memorize those rules. Now let's talk about the graphs of exponential and logarithmic functions. The graph of the function, the exponential function 3 to the x, and the graph of the logarithmic function with the base 3 are inverses of each other. So first we'll think about the graph of 3 to the x, and we can compare that to the graph of the logarithmic function by reversing all the x's and y's. Remember that inverse functions switch the x's and y values. So now each point from our exponential function can be reversed with the x's and y's to get points on our logarithmic function. The point -2, 1/9 becomes the point 1/9, -2. -1, 1/3 gets switched to 1/3, -1. 0, 1 becomes 1, 0. And 1, 3 gives us 3, 1. We can graph these on the same set of axes, and we can look at these points point by point. The point up here is where, on the exponential function, is where x was 1, y was 3. So on the logarithmic function, we get x is 3, y is 1. Then the point 0, 1 on our exponential function is the point 1, 0 on the logarithmic function. When we were back 1, we were up 1/3. So for the logarithmic function, when we're in the x direction 1/3, we're down 1. And finally, when we go back 2, we're up 1/9. So in the logarithmic function, when we go forward 1/9, we go down 2. Note that these two graphs are symmetrical, which means they have a mirror image around this diagonal line. Now let's look at some characteristics of logarithmic functions. The domain of the logarithmic functions consists of all positive real numbers. So in interval notation, that's from 0 to infinity, not including the 0. The range of a logarithmic function consists of all reals from -infinity to infinity. If we look at the graph we just did, the logarithmic graph, you'll see that the possible x values are only in the positive side of x, but that the y values go all the way down to negative infinity and they work their way up to positive infinity. Now, it might not look like they're going up too fast. On our graph, the highest we see is about 1.5, but if you go out infinitely far in the x direction, you can go up infinitely far in the y direction. The second characteristic we want to look at is that the graphs of all logarithmic functions of the form log base b of x will pass through the point 1, 0. And the x-intercept will always be 1, and there will be no y-intercept. The third characteristic is that if b is greater than 1, then this graph will rise as we go to the right. The fourth thing is if b is between 0 and 1, then the graph will fall as we go from left to right. So it'll come down something like this. Fifth characteristic is that the graph of a logarithmic function, as we said before, it will approach but not touch this y-axis. So the y-axis, which is the line x equals 0, is a vertical asymptote. We usually graph it with a dotted line. We now want to think about the domain of a logarithmic function. To do that, we'll first go back to think about exponential functions. Exponential functions had domains of all real numbers and ranges of just the positive real numbers. So exponential functions, their range is the set of all positive reals. Because logarithmic functions reverse domain and range from exponential functions, then the range of the exponential will become the domain of our logarithmic function. Since the range of the exponential function is all positive, then the domain of the logarithmic function will be the set of all positive real numbers. Now, so far we're looking at the domain of a logarithmic function whose argument is simply an x, and that's the set of all reals. But we're going to look at functions that have more complicated arguments of the log. It's shown here as g of x, which simply means it'll be something more complicated that involves x. And so the domain of this function will be whatever makes g of x positive. So we set g of x greater than 0. Let's take a look at an example to have a better understanding of this. Find the domain of f of x equals log base 4 of x minus 5. Well, the argument of the log has to be positive, but that doesn't just mean that x needs to be positive. For instance, if x was a positive 3, 3 minus 5 would give me a negative 2, and I can't take the log of a negative. And so in order to find the domain of this function, we take the argument of the log, which is x minus 5, and we set it greater than 0. We then do the algebra. X minus 5 is greater than 0. We transpose the negative 5 to the other side, make it a positive 5, and so that gives us x is greater than 5. That's our domain. We want to write that domain using interval notation. So x greater than 5 means that the domain of our function f in interval notation is written as parentheses 5, comma, infinity, parentheses. Now remember, the parentheses is always written on infinity. The parentheses next to the 5 means that it's greater than 5 but doesn't include 5. We actually are done with this question, but we want to illustrate this domain by taking a look at the graph. Note that we found that the domain was everything greater than 5, and this is illustrated by this graph. Notice that we have a vertical asymptote at x equals 5. Therefore, all points on the graph of f have x coordinates that are greater than 5. Now we will look at something called common logarithms. Common logarithms are logarithms that have a base of 10. The function f of x equals log base 10 of x is usually expressed as f of x equals log x. We write log without the 10 when the base is 10. Here's an example. The percentage of adult height attained by a boy who is x years old can be modeled by this function, where x represents the boy's age and f of x represents the percentage of his adult height. Before we begin, let's note that log is written without a base, so the base is 10. Continuing to solve, we take our function, and when the boy is 10 years old means we want to substitute in f of 10, and that gives us an argument of the log of 10 plus 1. That becomes 11, and then we can type this on our calculator. Your calculator has an log button, which is a log of base 10, and that should work out to give you about 80%. This means that a 10-year-old boy has attained approximately 80% of his adult height. Here's a summary of the properties we learned earlier, written with a base of b, but we can also look at these properties in terms of common logs. Since common logs have a base of 10, you'll notice we don't write the 10 on any of the base of the logarithms, but they're essentially the same properties using tens. Now let's look at natural logarithms. The logarithmic function with base e is called the natural logarithmic function. The function f of x equals log base e of x is usually expressed as f of x equals ln of x, and we'll read that as natural log of x. Note that we write ln without the e when the base is e. Let's take a look at the properties of logs written in terms of the natural logs. This means that the base is e, so for each of the logarithms we will write ln without the e written down below. And these are the same four properties as we had with the generic base of b, but they're written in terms of e. Let's take a look at an example. When the outside air temperature is somewhere between 72 and 96 degrees, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. This function models the temperature increase in degrees Fahrenheit after x minutes. Before we begin the problem, note that they're using ln, which tells us that the base is e. So we'll take our equation. They want to know the value when x is 30 minutes. So we substitute in the 30. And on your calculator, you have an ln button. This is a logarithmic button with a base of e. You should get approximately 34. And this tells us that the temperature will increase by approximately 34 degrees after 30 minutes.